Quantifiers. Quantifiers are the final step in our description of the building blocks that first order, that is, predicate logic, formulas are built up from. With quantifiers, we can finally describe a wealth of phenomena around us, inside computers and in mathematics. A famous example of the use of quantifiers is the so-called epsilon-delta definition of continuity. According to this definition, a function f on the real numbers is continuous at x0 if for every epsilon greater than 0 there is a delta greater than 0, such that for all x, if the distance between x and x0 is less than delta, then the distance between fx and fx0 is less than epsilon. Let us recall that first-order formulas are built up from atomic formulas by means of logical operations negation, conjunction, disjunction, implication, equivalence, existential quantifier, and universal quantifier, and parentheses are used for clarity. Thus, first-order formulas are of the form atomic, that is, x equals y or pnx or rxy, negation, conjunction, disjunction, implication, equivalence, universally quantified formula, or existentially quantified formula, where A and B are first-order formulas. Parentheses are used just as in propositional logic, for clarity. Thus, for example, if we want to put a universal quantifier in front of A implies B, we write for all x, left parenthesis A implies B, right parenthesis. Here are some examples. P0x implies P1x. Negation, left parenthesis x less than y or y less than x, right parenthesis. Exists x, left parenthesis x e y, and exists z, left parenthesis x e z, and not z e y, right parenthesis, right parenthesis. For all x, left parenthesis, bx implies exists z, left parenthesis, yz, and z less than x, right parenthesis, right parenthesis. Universal quantifier explained. The intuitive meaning of for all x a is that every value of x satisfies a. As in the sentence, every tile is red. Every x satisfies x squared greater than or equal to 0. All vertices x and y are neighbors. All men are mortal. Everybody loves her. Existential quantifier explained. The intuitive meaning of exists xa is that some value of x satisfies a. As in, some tiles are red. Some real numbers x satisfy x squared equals 2. Some vertices x and y are neighbors. There is a yellow tile. There is a vertex with 2 neighbors. In order to define when an assignment satisfies a quantified formula, we need the concept of a modified assignment. From any assignment S and variable x, and any element A of the universe of our structure, we can form a modified assignment S A/x as follows. Here is an example. On the first row we have S. S gives x value 1, y value 5 and z value 1. On the second row we have a modified assignment. S has been modified at x to 2. This is denoted S2/x. This modified assignment gets at x value 2, but in the other variables it gets the old value, so y gets value 5 and z gets value 1. On the third row there's a different modified assignment. In this case S has been modified at z to 8. It is denoted as 8/z. So this modified assignment gets at x value 1, which is the old value of S. At y it gets value 5, which is again the old value. And at z it gets the modified value, which is 8. Thus the assignment SA/x is like assignment x, except that the value of x is changed to a. Now we can define when an assignment satisfies a quantified formula. In this definition we use the concept of modified assignment. An assignment S satisfies for all xa in M if the modified assignment SA/x satisfies A in M for every A in M. Respectively, an assignment S exists xa in M if the modified assignment SA/x satisfies A in M for some A in M. We have now defined in full generality when an assignment S satisfies a formula A in a structure M. When this is the case, we write M satisfies subscript S A. This is called the Tarski truth definition, according to the Polish-American logician Alfred Tarski. With this notation, we can rewrite the above definition as follows. We have a table for all the cases of satisfaction. For an equation, S satisfies x equals y in M if and only if Sx equals Sy. S satisfies Pnx in M if and only if Sx is in the set Pn M. S satisfies Rxy in M if and only if the pair Sx, Sy is in the relation Rm. S satisfies negation A in M if and only if S does not satisfy A in M. S satisfies A and B in M if and only if S satisfies A and S satisfies B. S satisfies A or B in M if and only if S satisfies A or S satisfies B in M. S satisfies A implies B in M if and only if S does not satisfy A or S satisfies B in M. S satisfies A equivalence B in M if and only if either S satisfies A and S satisfies B in M, or S does not satisfy A and S does not satisfy B in M. S satisfies for all xa in M if and only if for all A in the set M, the modified assignment SA/x satisfies A in M. Finally, S satisfies exists xa in M if and only if for some element A of the set M, the modified assignment SA/x satisfies A in M.